Hello students, let us start our discussion about different condition in LCR series circuit. So for this we have an inductor and a capacitor and a resistor, and they are connected in series through a variable or alternating potential source V, that is equal to Vm sin omega t, where the angular frequency of the AC potential source applied is omega. And after calculation, we have obtained that at an instant of time t, the amount of the current flowing through LCR series circuit is obtained as I equal to Im sin of omega t plus phi, where Im is equal to Vm by Z. This can be further written as Vm by under root R square plus Xc minus XL whole square, and this phi can be expressed as tan inverse Xc minus XL divided by R. So these are the two different equations. One is V equal to Vm sin omega t, and the second one is I equal to Im sin omega t plus phi. With the help of two different equations, we can discuss different aspects of LCR series circuit, in which the first aspect is resonance. So we know that if the amplitude of the current flowing through this LCR series circuit becomes maximum at any instant of time, then what will be the criteria at which the current flowing through LCR series circuit becomes or reached at its maximum value without changing the inductance of this circuit or capacitance of this capacitor and resistance of this resistor. So this will happen only by the changing of the frequency of the applying potential source across this LCR series circuit. So if we change this value of omega, then as we know that XL is equal to omega L and XC is equal to 1 upon omega C. And from here we are seeing that Im is equal to Vm by Z, means Vm by root of R square plus Xc minus XL square. So if we reduce the value of this Z, then we can get the value of this current is as maximum. For reducing the value of this Z in this circuit, so we have to equate the both term, that is the capacitive reactance and the inductive reactance of the circuit. This inductor has a inductive reactance that is given by the formula omega L, and this capacitor has a capacitive reactance that has a formula of 1 upon omega C. So from here we are seeing that the inductive reactance of the circuit is directly proportional to omega. It means XL is directly proportional to omega if we take L as constant. So if we plot a graph between omega and XL, then we know that when we increases the value of omega, then the value of XL is also increases, and at the value of omega becomes 0, the value of XL is also becomes 0. It means the inductive reactance becomes 0 when the potential becomes DC potential source. It means the frequency of the alternating its polarity becomes disappear. So when omega becomes 0, so value of XL is 0. So when we plot a graph between omega and XL, then we get the graph is like this. This is a straight line. And also if we plot a graph between XC and omega, then we are seeing that XC is inversely proportional to omega. It means XC is proportional to 1 upon omega if we take C as constant. Okay, so in this we obtain a particular reciprocal graph. It means when we increases the value of omega, then there is a relevant decrement in the value of the capacitive reactance, and when we decreases the value of the omega, means angular frequency of AC potential source, then there is a relevant increment in the inductive capacitive reactance. Okay, so if we plot a graph, then we get when omega is 0, then XC is infinite. It means this does not touch at any point at here. So if we place this at this point, then what will be the value of or the plot of this graph? This will be like this. Okay, so this is a particular graph representation of the XC inversely proportional to omega. Now let us come to our topic for which we want to discuss. If we change the omega applied across the LCR series circuit, it means when we change the frequency, angular frequency of the AC potential source which is applied across the terminals of LCR series circuit, then we can find out the value of XL will also change and XC is also changed. But suppose that if at any value of omega, if we find out XC is greater than XL, suppose that if we obtain at any frequency omega, at any value of angular frequency, that is omega, if we obtain that XC is greater than XL, then we want to reduce this value of Z, for which we make this XC minus XL as equal to 0. It means if we equate this XC just equal to XL, then the term XC minus XL from the Z becomes disappear. So for this we have to increase. It means for during increasing the value of omega, during increasing the omega, we get at any omega naught. Suppose that if we increases the value of omega, then we get a particular frequency omega naught at which XC becomes XL. Then this XC means 1 upon omega naught C, that becomes XL, that is omega naught L. So from here we can easily calculate for value for this omega naught from here. So the value of omega naught square is equal to 1 upon LC. So from here omega naught will be equal to 1 by root of LC. So this is a particular frequency at which XC becomes just equal to XL, and at that frequency the Z becomes R. It means at omega naught Z becomes R. So IM becomes VM by R. So as we know that the minimum value of the impedance of any LCR series circuit will be just equal to the resistance, and in either case of either value of omega, the value of z is always greater than the value of this r. So in the case at the value of z is equal to r, the value of the current flowing through this LCR series circuit becomes maximum. So this can be represented by the symbol Im max. So Im max is equal to Vm by R. Okay, so this is the maximum amount of the current which is possible to flow through the LCR series circuit. And when this current flows through LCR series circuit, then the circuit is said to be at resonance condition. And when Xc is equal to Xr in LCR series circuit, then we can say that resonance occurs. So the criteria of the resonance is Xc is equal to Xl, and at resonance the value of the current flowing through LCR series circuit becomes its maximum value, and the maximum value of the current will be given by the formula Vm by R. Okay, so this is a small discussion of the resonance. Now let us understand this with the help of small numericals. Suppose that we have an inductor of value 1 millihenry and a capacitor of 1 microfarad connected in series, and a resistor of 100 ohm. To any potential source we equal to, suppose that 220 sine of 2 into 10 to power 6 t. Okay, so if we want to plot a graph for the current at the condition of resonance and at different value of frequency, then we can easily plot this. Now what will be the value of the current at resonance? So at the value of resonance, the value of the amount of the current becomes Im equal to Vm. This is 220 divided by 100. It means 2.2 ampere. And at any other value of the frequency, the amount of this current is always less than the value of this. So if we plot a graph for this, then we can find out, suppose that this one is the 1 ampere, this one is the 2nd ampere, this is the 2.2 ampere. So at omega naught, if the potential across this will be just equal and opposite to the potential across this, then the total potential drop will occur in the resistor. So at that time the current flowing through this LCR series circuit becomes maximum. So suppose that by plotting the current with respect to frequency, which can be changed during time, then we will obtain the value of the current, the amplitude of the current at resonance is maximum. And when we obtain the amount of the amplitude of the current at different frequency, then we will obtain it is smaller in comparison to at that of the resonance frequency. Okay, so this is a particular case. Now if we talk about when we replace this resistance by a 200 ohm resistor, then the amount of this current will reduces, and that becomes 220 divided by 200, it means 1.1 ampere. So if we plot the graph for this current at a particular frequency, at that same frequency, but when we replace this resistor by a 200 ohm, then at that same frequency the amount of current will obtain at this value, it means 1.1 ampere. So from here it is clear that when we change the, when we increases the resistance applied in LCR series circuit by twice of its initial value, then the amount of the maximum current flowing through the LCR series circuit reduces to its half of the maximum value. Okay, so this is a simple case by which we can understand the resonance easily. Now let us discuss the sharpness of resonance.